aspect of current basics. The first problem of the sheet is about a frame of this kind. This is a frame which is constituted out of two equilateral triangles ACD and CDE, side being 1 meter each. And in every element of this frame, a current I is flowing. I is given to be some value, whatever it is, I do not know. How much is I given to be? 2 amps. I is given to be 2 amps. And there is a magnetic field exposure B going into the plane of the board of magnitude 4 Tesla or 4 Tesla. We want to be able to compute the force. We want to be able to compute the force on this frame, total force on this frame. What do you think you would do? What would you want to do here? How would you best compute the force on this frame? Now, see, one way to do is, a very shoddy way to do is, I compute the force on every element. Every side, I compute the force and I do a vector addition of that. That's one way to handle that. That's very shoddy. That's extremely shoddy. If you recall, if this was any current carrying wire, PQ, right, carrying a current I, then the total force that this experiences is like I PQ cross B. If it was exposed to a uniform field, then this shape does not matter. It's only if B is constant, see, if B is constant, then the sum of all the I dl cross B's is as follows. The B will wriggle out, I will come out, integral dl. dl's are these elements. dl's are these elements, right? These are my elements dl, and then cross B. But the vector sum of all these dl's will be PQ. The vector sum of all these dl's will be PQ. So I PQ cross B would be the total force acting on it. Yes or no? Right? Now, so think of it like this. The force acting on CD is what? I CD cross B. CD cross B. Right? Which is what? That's a force acting on CD. So magnitude of this, and realize that CD and B are perpendicular. CD is of length L. So it will be simply like BIL. BIL is the force acting on CD. And how does it act? These are my DLs. B is going in. So DL cross B would be upwards. Do you realize that? This is DL in the direction of the current. B is going into the plane of the board. Right? These are my DLs. B goes into the plane of board, so DL cross B would be upwards. That's a force acting on CD, yes or no? That's a force F acting on CD, which is BIL. And it's upwards, yes or no? Now, if you look at CAD, hey, the force acting on CD, just like this, is like same as CAD is the same as the force acting on CD, isn't it? It does not depend on, this shape. It will only depend on CD, right? So the force acting on CAD will also be this. And look at this, CED. The force acting on CED from the same principle will be the same as the force acting on one single straight element CD. Yes or no? So force acting on ACD is the same as the force acting on CD, is the same as the force acting on CED. So essentially the total force acting on this would be 3 times the force acting on CD. 3 times the force acting on CD, yes or no? Which is like 3 BIL. How much is, whatever this turns out to be. B is given to be 12, I is given to be 2, length is 1. So that makes it 24 newtons is the force acting on this entire frame. It's simply 3 times the force acting on CD. Because one, the force actually acting on CD. The force acting on CAD is the same as the force acting on CD. So that's 2 times the force acting on CD. And then CD, force acting on CD is the same as force acting on CD. That makes it 3 times the force acting on CD. The force acting on CD is computed by BIL because DL and B's are perpendicular. And this force would be upwards. This force would be upwards because DLs are like this. B is plunging into the plane of the board. So my DL cross B will give me the direction of the force, which is upwards. So 24 newtons net upward force acting on this frame. 24 newtons net upward force acting on this frame. Yes or no? Clear? Right, so the next problem is about a copper wire. I'm assuming it's a solid copper wire of radius r given by 0.8 into 10 to power minus 3 meters. And it carries a current I whose value we do not know. Now, in the surrounding region, this copper wire will produce a magnetic field. It is found that the maximum magnetic field produced by this copper wire carrying current I, long, infinitely long, is 5 into 10 to power minus 3 Tesla. The maximum. It produces a variable magnetic field in the surroundings. But the maximum value of the magnetic field that it produces in the surroundings is 5 into 10 to power minus 3 Tesla. And we want to be able to find the current through this. We want to be able to find the current through this. Now, what I do is, first of all, let me look at some point at a distance small r from the axis of this copper wire, right? So, I imagine a coaxial cylinder of radius small r, right? Now from symmetry, B at every point of the surface of this chosen cylinder would be same in magnitude, right? And it will be tangential, right? If the current is like this, it will be tangential at every point circulating like this. It will go this way, right? So the B dot dl, if I choose a loop like this, and I do a B dot dl this way, what would that be? B into 2 pi r. That will be the sum of all the B dot dls through this loop, right? And that must be equal to mu naught times I enclosed, I inside this, right? So that's going to be I by pi r squared into pi r squared. Yes or no? That's the current through this. The total current through an area pi r squared is this. So current per unit cross-sectional area into the cross-sectional area of this. That's the current flowing through this. Mu naught I enclosed. Yes or no? So do you see that this B is some constant times r? Because everything else is a constant. This r will, 1 r will get cancelled. So B is linearly varying with r inside the cylinder. B is varying linearly with r inside the cylinder. That means inside the cylinder, B varies, B increases linearly with r. B increases linearly with r. Now this, it assumes the largest value on the surface, right? And now once you move out of the surface, so when this is so this is for r inside the cylinder, small r inside the cylinder. That means this is for r less than or equal to capital R. But if I take r greater than r, then what happens? This is my cylinder of radius capital R, right? Now if I take a loop like this, of radius r greater than r, then sum of all the B dot dls on this loop is going to be what? B into 2 pi r. And that will be equal to mu naught times the total current I enclosed, Ampere circle law. So this time you see that B is some constant C prime by r. B decreases with r. B then decreases with r hyperbolically, right? That means up to r it's increasing linearly. From the surface it decreases. That means it assumes a maximum value on the surface. So on the surface for small r equal to capital R, it assumes a maximum value. And on the surface, what's going to be B? B is going to be mu naught I divided by 2 pi r. That's going to be the B on the surface, which assumes its maximum possible value, and that's given to be 5 into 10 to power minus 3 Tesla. That's given to be 5 into 10 to power minus 3 Tesla. You can obtain the value of I from this. You can obtain the value of I from this. B on the surface would be the largest, and it's given to be this much. And you must recall this result for, you know, a solid cylinder carrying current which is uniformly distributed over the cross section. From the center to the surface, it will increase linearly, and then it will fall as 1 by r. It will fall as 1 by r. Maximum on the surface. It assumes its maximum value on the surface, courtesy Ampere's circuit law. Right? Make sense now? So we have an electron which is moving with a uniform velocity v naught along the x-axis. Uniform velocity v naught along the x-axis. And it's subject to two fields. There is an electric field in the negative y direction. There is an electric field in the negative y direction. Uniform electric field in the negative y direction. And there is presence of a magnetic field in some direction. The two fields connive to produce no net force on the particle. When they produce no net force on the particle, the acceleration is 0, and therefore the velocity will be preserved, will be maintained constant. That means the net of electrical forces and magnetic forces must add up to 0. So the net of both the forces, Q is the charge on the electron, QE plus Q into, let's say, V is the velocity which is along the x-axis cross B. That must be 0. That must be 0 on the electron. That means E must be minus of V cross B. E must be minus of V cross B. Now, E is like, this direction of E is like along I cap. No, sorry, minus j cap, beg pardon, minus j cap. And V is along I cap. So this is like some I cap cross. Now I want to fill up this space. So the minus will anyways get cancelled. I cross what will give me j? Minus k. I cross minus k. I cross minus k will give me j. Minus got cancelled, so I have j giving me I cross some vector. I cross what vector will give me j? Minus k. You know, I cross minus k will give me j, isn't it? K cross I is j, so I cross minus k will, right. So then B must be in the minus k direction. That means in the negative z direction. B must be in the negative z direction. Do you all understand this? B must be in the negative z direction. So there is a charged particle, charge q mass m, which enters a region of a magnetic field making an angle 45 degrees, right? And then we know that the path of this particle is going to be helical, right? There is going to be the pitch of the helix, and there is going to be the radius of the circular strands, right? So given P, we want to find R. Given P, we want to find the radius of the helix. Now, extremely simple. Realize that the radius of the circular part is going to be, there is a V perpendicular, which is V sine theta, and there is a V parallel, which is V cos theta, right? Radius is this perpendicular component along with B will produce a circular path, and that's going to be M V perpendicular V sine theta by QB, right? We are aware of this, right? The time period is going to be 2 pi m by QB. That's going to be the time taken for 360 degrees of rotation, right? And the pitch is given by V parallel into T. That means V cos theta into T, which means 2 pi m by QB into V cos theta. That's the pitch. That's the pitch of the helix, right? Now, cos theta and sin theta are equal because theta is 45 degrees. So mv sine theta by qb is the same as mv cos theta by qb, isn't it? Because theta is 45 degrees, mv cos theta by qb is the same as mv sine theta by qb. So this mv cos theta by qb I can write as r. Because theta is 45 degrees, cos theta and sin theta are equal. So mv sine theta by qb is the same as mv cos theta by qb. So mv cos theta by qb I write as r. So this is like 2 pi r. So r will be p by 2 pi. R will be p by 2 pi. The radius of the helix is going to be pitch divided by 2 pi, in this case for theta equal to 45 degrees. Because cos theta and sin theta are equal. Clear? Right. So this time we have a hollow cylinder. This part is hollow up to r1 units. From the axis it's hollow. And then from r1 to r2 there is current flowing in the annulus region. In the annulus there is current flowing. Right. So if I is the total current passing through this, then the current per unit area of cross section in the material of this is going to be what? I divided by pi r2 squared minus r1 squared is the current per unit area, cross sectional area, right? Current is flowing in this only, this region, r2 minus r1. So area of this region is going to be what? Area of this cross section is going to be pi into r2 squared minus r1 squared. Pi into r2 squared minus r1 squared. Now, I want to find the variation of, so there is current I which is flowing through this. Now I want to find the variation of the magnetic field with distance from the axis. Variation of magnetic field created by such a current carrying wire flowing through this annulus as a function of distance from the axis. So first of all, in this innermost region, in the hollow region, that means for r less than or equal to r1, r less than or equal to r1. Very simple. If I look at an Amperian loop this way, if I look at an Amperian loop this way of radius small r, then B at from symmetry, B at every point is going to be the same, and I circulate the loop like this, then the sum of all the B dot drs is going to be B into 2 pi r. That's going to be mu naught times the I enclosed. I enclosed is 0. So that gives me B equal to 0. That gives me B equal to 0 for r inside this, inside the hollow region. B is 0. Right? Now, for r greater than r1 less than or equal to r2. R greater than r1 less than or equal to r2. What happens to the magnetic field? Okay, so this time I'm going to take an Amperian loop this way. Let me take an Amperian loop like this. This is r. Again from symmetry. And I circulate the loop this way. Then sum of all the B dot drs is going to be, B dot dls is going to be what? B into 2 pi r. Right? So B into 2 pi r. That's going to be mu naught times the current enclosed. Now current would be from this point to this point. That means in this region is going to be the current, right? In this cross section is going to be the current. What is this? This is like pi into r squared minus r1 squared divided by I by pi into r2 squared minus r1 squared. That's the current enclosed. Do you realize what I've done here? Hey? Do you know what I did here? Not sure, na? B dot dls is going to be B into 2 pi r. Current enclosed. Now current per unit cross sectional area is pi into r2 squared minus r1 squared. That's the current per unit area. So that's the current per unit area, I by pi into r2 squared minus r. Into this area. What's the area of cross section through which the current is flowing in this Amperian loop? Well, from r1 to r. From r1 to r. From r1, this is r1, this point is r1 to r. Right? So that's like a pi into r squared minus r1 squared. Current per unit area into area. Area is from r1 to r. That's a cross sectional through which current is flowing. Mu naught I enclosed. Yes or no? Very clearly this then is like B is like, so all, you know, I combine all the constants. So some constant into r squared minus r1 squared divided by r kind of a thing. some constant into r squared minus r1 squared by r. That is from r1 to this surface, from r1 to r2, from r1 to r2, this is the variation of B. Yes or no? And then for r greater than r2, for r greater than r2, am I confusing you? No? That means this time I take an Amperian loop of this kind. I take an Amperian loop of this kind. B dot ds would be B into 2 pi r. That's going to be mu naught times, now the entire current I is enclosed. So this time B is going to be some constant C prime by r. It falls as 1 by r. Right? Now let's draw the graph of B versus small r. Let's draw the graph of B versus small r. I hope all of you understand this. Right? So, this is B versus small r. Now, up to r1 it's 0. Up to r1 it's 0. You see, B is 0 up to r1. That means up to r1 it is 0. Inside the hollow region, it's 0. Right? Now, this is from r1 to r2. This is from small r equal to r1 to r2. So, do you realize this can be written as r minus r1 squared by r for this region? That means now here to here. You know? R minus. So, if r is increased, this part will increase. This will decrease. So, difference will increase. Yes or no? This difference will increase. As small r is increased, this will increase, but this will decrease. So, difference will increase. So, then there is obviously a non-linear increase in r. Right? Up to r2. That increase takes place up to r2. Up to the surface. And from the surface onwards, this is the variation. It decreases. It decreases from the surface. This is the variation of B versus small r. Check with the options. See. There is this loop. PQP is this loop carrying a current I. And it subtends an angle theta smaller than 180 degrees. I want to find the direction of the magnetic field at O. I want to be able to find the direction of the magnetic field at O. Now, if theta is less than 180 degrees, O obviously will be outside this loop, will be outside this loop. You know, if theta was greater than 180 degrees, A would have been inside the loop. See? You know what I'm saying, Trishanu? Say if theta was greater than 180 degrees, if this was theta, this was my loop, PP. This time theta is more than 180 degrees and the center would be inside the loop. The center would be inside the loop. Right? Yes or no? I'm sorry. Make it like this way. Center would be inside the loop if theta was more than 180 degrees. This is how it happens, right? So, theta less than 180 degrees, the center lies outside the loop. Now, I will make a statement, but I want you to think about this. And this will apply irrespective. If there is any current carrying loop, and I want you to be able to obtain this yourself. If there is any current carrying loop, then the field inside this loop will always be into the plane. Say if it is clockwise like this, if it is clockwise like this, this is clockwise current carrying loop, then the field inside this loop would be into the plane of the board, will be into the plane of the board, let me tell you, if it is clockwise. And it will be out of the plane of the board, clockwise hoga to. But if it is anti-clockwise, this is the current ACW, then inside the loop it will come out of the plane of the board, and outside the loop it will go into the plane of the board. You should be able to obtain yourself. I'm saying in general, and this will apply unconditionally. unconditionally. If there is a current carrying loop, and if the current is clockwise, planar loop, I'm talking of a planar loop, and the current is clockwise, then the field inside is going to be into, the field outside is going to be out of the plane, right? And if it is anti-clockwise, the field inside is going to be out. Curl your fingers in the sense of the current and watch your thumb. It's going to be out of the plane of the loop. But outside, it's going to be into the plane of the loop. Think of this from a dipole moment perspective. Think of it from a dipole moment perspective. You'll be able to obtain that. Every current carried loop behaves like a magnetic dipole, Think about it from that perspective. Now, and I want you to really obtain it independently. So if this is my loop, it's clockwise. So field inside is going to be into, and field outside is going to be out. So at O, the field will be out of the plane of the board. At O, the field will be out of the perpendicular, in both cases perpendicular, but out of the plane of the board in this case. And if theta was greater than 180 degrees, then what? O will be inside. If theta was more than 180 degrees, you will have O inside. And then the field would have been into the plane of the loop if theta was more than 180 degrees. Got me? Sounds good? Right? In the y direction. Uniform magnetic field, be not in the y direction. Right? There is a particle which is projected towards the origin along the x-axis, along the negative x-axis from a point D00, right? We want to be able to find the minimum D, minimum V, or rather the maximum V for which the particle does not hit the YZ plane. This is my YZ plane. I don't want it to hit the YZ plane. Clear? What can be the maximum? Of course, you know, if you go on increasing V, its prospect of hitting the YZ plane increases. So there is a limit to which you can increase V so that it still does not hit the YZ plane. Now, first of all, tell me this. This V and this B will connive to do what? Is it a positive charge? Or a negative charge? Let's assume positive. So there is B naught upwards and there is V like this. V and B are perpendicular. What would happen? Circular trajectory. The plane of the circle will be hit by the B lines. Normally, the plane of the circle will be hit by the B lines. Normally, that means if the B lines are in the Y direction, then the XZ plane would be the plane of the circle? Yes or no? XZ plane would be the plane of the circle that the particle executes. Why circle? Circle because V and B are perpendicular, so it will execute a circular trajectory. And the plane of the circle is hit by the B lines normally. If B lines are in the Y direction, the plane of the circle must be the XZ plane. XZ plane is perpendicular to the Y direction. Yes or no? Right?
What about its weight?
No, we'll assume that it's balanced. It's on a horizontal plane, and that's balanced by the normal reaction. If nothing is, nobody tells you that gravity is acting downwards. We are assuming that gravity is balanced. All right. So for all practical purposes, if nothing is given, you assume that XZ plane is the horizontal plane, and the normal reaction from the ground balances the weight. Right? So, what would be the radius of the circular trajectory? mv by qb. mv by qb would be the radius of the circular trajectory. And v cross b goes into the plane of the board. V cross b goes into the plane of the board. Yes or no? Isn't it? V cross b, that means the center of the circle would be in the negative z direction. Yes or no? Right? This would be the center of the circle, say. This is V. B is like this. So this line is parallel to the z direction. This line is parallel to the z direction. This is my negative z direction. So V cross B would go in the negative z direction. In the negative z direction. Which means what? Would you then want to believe that if this is the center, this distance, for it to not hit the YZ plane, this distance should be larger than the radius of the circle. This distance will be larger than the radius. This distance should be larger than the radius. See? Right? Right? This distance should be larger than the radius. Why? So that it doesn't hit the YZ plane. It is not supposed to hit the YZ plane. The plane of the circle will be the YZ plane. Plane of the circle. How? Let me explain it to you with this notebook. Come. I mean, in case you want me to do that. This is the z direction, this is the x direction, this is the y direction, right? I launch the particle here like this. B is like this. This is V. This is my x-axis, right? And this point is D00. This is V. This is B, right? V cross B is like this, right? That means the center lies somewhere here. And this is my YZ plane. I don't want it to hit the YZ plane, isn't it? This is my Z direction, this is my Y direction. So if I'm launching it, realize that this would be the circular trajectory. If this is the center, this would be the circular trajectory. And this maximum displacement in this direction will be the radius. Like this. Yes or no? So if the maximum displacement is the radius, and if this radius is less than D, it will not hit this YZ plane. Samajh gaya? I'll explain again. This is V, this is B, right? V cross B goes into. So when you are launching it from this point, the center lies somewhere here. The center lies somewhere here. This is the radius, mv by qb. And now the particle takes up a trajectory like this. Like this. Thoda sa aise. Particle takes up a circular trajectory like this. Right? This is my YZ plane. So the radius of the circle should be less than D. The radius of the circle, see, this is the center of the circle. The particle goes this way, isn't it, in this plane? So obviously the radius of the circle should be smaller than D. The radius of the circle, this is the center, this is the radius. Radius has to be less than D, isn't it? Huh? Difficult to draw this there, but I hope you understood what I said, huh? Got me, na? So the radius of the circle has to be less than or equal to D. That means V has to be less than or equal to QBD by M. QBD by M. So what's maximum V? QBD by M is the maximum V. Right? QBD by M is the maximum V, so that it doesn't hit the YZ plane. Clear? There is a current carrying wire like this, infinitely long, and there is a wire PQ perpendicular to this, and it carries a current I2, right? Now if you look at any element of this in the direction of the current, this is my DL, this is the direction of DL. At this point, this current carrying element is exposed to a magnetic field because of this current carrying element. And do you realize the magnetic field on this DL would be into the plane of the board because of this current carrying element? Because of this current carrying element, the magnetic field on DL would be into the plane of the board. Do you realize that? This is DL cross R going into, right? Now if B is into, this is my DL, B is into, right? B is into, this is DL. So DL cross B would be the direction of the force acting on this current carrying element, which would be upwards. It will experience an upward force, right? DF. So all the DLs experience an upward force. All the DLs experience an upward force. So the net force would be upwards, right? So for sure not in translational equilibrium. Also, this DF produces a non-zero torque about this wire. Produces a non-zero, this DF acting on this produces a non-zero torque. DF into this length is a non-zero torque produced about this wire. Yes or no? That means there is non-zero torque acting on PQ, and that non-zero torque acting on PQ will produce rotational motion. So PQ will get into general rigid body motion. There is going to be translation and as well as rotation. There is going to be translation as well as rotation. Why translation? Because these DFs are all upward, acting on various DLs on PQ. So there is a net upward force acting. So there is no translational equilibrium. Every DF produces a torque about this point. So there is a torque in this sense acting on every DF in this sense, right? So there won't be rotational equilibrium. There is going to be rotational motion as well. So PQ will have translational motion because the net DFs don't add up to zero. And since the net torque is not zero, it will also have rotational motion. It will also have rotational motion. So translational as well as rotation. Yes or no? Current carrying wire, carrying current I and of length L. We want to compute the magnetic field at the point P. Very clearly, if this is L, very clearly this is 45 degrees, this is 90 degrees. And at this point P, we want to compute the magnetic field. It's a direct formula. The magnetic field at the point P is going to be mu naught I divided by 2 pi L into cos pi by 4 plus cos 90 degrees divided by 2. So which is like mu naught I divided by 4 pi L, and cos pi by 4 is 1 by root 2. That's the magnetic field. And what's the direction of this field? Very clearly, you know, our DLs are like this. These are our DLs and these are our Rs. So DL cross R is into the plane of the board. So every DL that constitutes this current carrying wire, the DL cross R is going to be into the plane of the board. So this magnetic field is into the plane of the board. Yes or no? Right? Thank you. We have a non-conducting circular disk of radius r centered at C, and charge q is uniformly spread on the surface of this disk, and it's given an angular velocity omega about its axis. We want to be able to compute the magnetic moment of this disk. What we do is we use the formula magnetic moment mu by angular momentum L is charge q divided by 2m. Is q divided by 2m, that's the gyromagnetic ratio. So then that gives us like mu equal to, and what's L? L for this is like half mr squared for a disk, right? So replacing L by half mr squared, we get like a mu equal to L, which is half mr squared into q by 2m. Q by 2m. So that makes it like a m will get cancelled, 1 into omega. Half mr squared into omega, that's the angular momentum. I omega, I about this axis is half mr squared. So I omega is the angular momentum. So I have an omega here. So that makes it like 1/4 q omega r squared. That's the magnetic moment of this disk, right? Thanks. So there is a square loop carrying current I. Square loop of side A carrying current I, and it's exposed to a magnetic field plunging into the plane of the board, right? Now keeping the total perimeter the same, the square is converted into a circle of radius r. The square is converted into a circle of radius r. So obviously, you know, the circumference of the circle 2 pi r must be 4a. So the radius of the circle must be 2a by pi must be the radius of the circle. Yes or no? 2a by pi must be the radius of the circle. Now, and it's exposed to the same magnetic field in the field itself. This is done. Transformation from a circle, from a square to a circle takes place, right? We want to compute the work done in the process, by an external agent, to accomplish this change. Work done is always what? Change in potential energy. It's in a conservative force field, there is going to be potential energy of the system. So work done would be change in potential energy. Meaning final potential energy minus initial potential energy, that's going to be the work done. Now, a current carrying loop, if there is a current carrying loop in general, and it's exposed to a magnetic field B, it's exposed, let's say, to a uniform magnetic field B, in any manner, not necessarily into, then there is potential energy associated with this loop. How does one compute the potential energy associated with a current carrying loop? Minus mu dot B, have I told you this? Torque is mu cross B, potential energy is minus mu dot B, right? So the potential energy of this loop is going to be minus mu dot B, where what is mu? Mu is the magnetic moment of the loop. And how's the magnitude of mu computed? I into the area enclosed, right? And the direction of mu, how do you obtain the direction of mu? You curl your fingers in the sense of the current, watch your thumb. That will be the direction of mu. The magnitude of mu would be I into the area enclosed. The direction of mu is going to be obtained by curling your fingers along the sense of the current and noticing your thumb. The thumb will give you the direction of mu. Yes or no? The vector mu, magnetic moment vector for a current carrying loop. And then the vector mu dot B with a negative sign will give you the potential energy of a loop. Yes or no? Okay. So our task is simply to compute the potential energy of this and the potential energy of this. So first things first. What is the magnitude of the magnetic moment of this loop? I into 4 into A squared. I into A squared is the magnetic moment of the loop, right? Potential energy, let's say initial potential energy is going to be minus mu1 dot the magnetic field vector, right? Now, what is the angle between mu1 and B in this case? 0. Because see, curl your fingers in the sense of the current, watch your thumb, that's the direction of mu and that's also the direction of B. So if I take the dot product, it will be mu1 into B into cos 0, mu1 into B into cos 0. So that's like a minus mu1 into B into cos 0, which is 1, right? So which is minus IA squared into B, that's the initial potential energy, right? Angle between mu is going into, plane is also into, so when you take the dot product, cos 0 is what will appear, right? Now in this case, what's the magnetic moment? I into pi r squared, pi into 2a by pi whole square, which is 4a squared I by pi is the magnitude. The direction into, right? It's going into the plane of the board, the direction of the magnetic moment. And B is also into. So the final potential energy is going to be again minus mu2 dot B, which will simply be minus mu2 into B, right? So which is minus 4a squared I by pi into B. That's the final potential energy. Work done is going to be final potential energy minus initial potential energy. Work done is going to be final potential energy minus initial potential. Do a difference of these two. That will give you the work done. BA squared you can take, BA squared I you can take common and perform the rest. Final potential minus initial potential energy, that's going to be the work done to transform this square into a circle, maintaining the perimeter same, maintaining the perimeter same. Do you realize whatever I've done here? There is a wire, a straight wire of length L, converted, a straight wire of length L, converted into a circle of radius R with n turns. With n turns. And then a current I is made to pass through this. A current I is made to pass through this. And the whole thing is exposed to a magnetic field. The whole thing is exposed to a magnetic field. B. Uniform, let me assume uniform magnetic field. Now, two things. It'll experience a torque, a current carrying wire, a current carrying loop when placed in a magnetic field experiences a torque. How do you get that torque? Mu cross B. Mu is the magnetic moment. Mu cross B. You have two options, two things with which you want to play around with. You can vary the number of turns. You can't change the length, but you have handle over the number of turns. How many turns you want to create? 1. 2. The angle between mu and B. Angle between mu and B, you can orient the wire at any angle theta with respect to the magnetic field B. So for sure the magnitude of torque is given by mu B sine theta then. Theta is the angle between mu and B. Now if you want to maximize torque, one thing for sure, theta 90 degrees, theta should be 90 degrees. The other thing, number of turns. Look, so this has to be maximized. This has to be maximized, right? The length L is like n into 2 pi r, isn't it? N into 2 pi r, right? So r then becomes L by 2 pi n. Yes or no? The area, therefore the magnetic moment of this is going to be n times Ia. N times Ia. If there are n turns, n times Ia. N times Ia would be the magnetic moment for a, right? N times Ia. N is the number of turns, I is the current, and A is pi r squared. That means L squared by 4 pi squared n squared. That's a magnetic moment, right? So we have this mu as pi L squared I by 4 pi squared n into B, which is constant, but theta could be varied. So to maximize tau, what are the two things you would do? You would minimize n you want to choose as 1, right? You should choose n as 1. To maximize torque, choose n as 1. If n is the smallest, then you will get the maximum torque, and choose theta as 90 degrees. So tau max is going to be what? Pi L squared I B divided by 4 pi squared. That means BIL squared by 4 pi. BIL squared by 4 pi is the maximum torque. Put n equal to 1 here and theta equal to 90 degrees to maximize the torque. That's a maximum torque that it can experience given a length L, given a current I, and given the magnitude of the magnetic field B. Do you understand this? Sure, na? This is the maximum torque that it could experience, right? Sounds all right? So the next problem is about a current carrying loop. This is a current carrying loop of mass m. This is the vertical direction. The y direction, let's say, belongs to gravity. And now I want to be able to apply in this region a uniform magnetic field. I want to be able to apply in this region a uniform magnetic field so that this fellow levitates. The force because of the magnetic field is balanced by the weight. How should the magnetic field be applied on the loop? How should the magnetic field be applied in this region uniform so that it balances the weight, so that there is no net force acting on the loop? I want the magnetic force to balance the weight. In what direction should I apply the magnetic field so that it could successfully balance the weight? The force because of the magnetic field balancing the weight.
So the I is in the opposite direction.
I like this. I don't have handle over I. I किसी भी direction.
If it is in the opposite direction, we get given question.
Okay. Okay. Let it be like this. Okay. This way, huh? Chalo, ठीक है. Now tell me, in what direction should I apply a magnetic field so that the force because of the magnetic field, uniform magnetic field acting on this loop, balances the weight. Balances the weight. What should be the direction of the magnetic field so that it balances the weight?
It has to be parallel to the plane of the wire.
Huh?
It has to be parallel to the plane of the wire first thing. Because sir, if the force is in this direction, the current is in this direction, then the magnetic field has to be in either this direction or this direction.
Positive z direction, you say? Okay, let's go back to the basics. Let's go back to the basics. If there is a current carrying loop, if there is a current carrying loop and it is placed in a uniform magnetic field, what's the magnetic force acting on it? 0. So no matter what the direction of the magnetic field is, the force acting on a closed loop placed in a uniform magnetic field will always be 0. See, the force is like I dl cross b, right? And the cross b comes out because b is constant, and the I comes out, and the vector sum of all the dls will be 0. In a closed loop, the vector sum of all the dls in a closed loop will be 0. So the net magnetic force on a closed loop exposed to a uniform b will always be 0. So which means magnetic force in this case can never balance the weight no matter what direction you choose. Yes or no? It can never balance the weight because it will always be 0. No direction, no magnitude will ever balance the weight in this case if B is uniform. Clear? There is an equilateral triangle carrying a current I, like this. Alright? And I want to find the magnetic field at O. So look at one side. What's the magnetic field at O because of one side? B1 is going to be mu naught I by 2 pi r cos alpha plus cos beta by 2. That means 2 cos 30 degrees divided by 2. And these are my dls, these are my r's. In this case, dl cross r comes out of the plane of the board. Do you realize that? dl cross r, bio savard, dls, this is my dl, this is my r, dl cross r comes out of the plane of the board. So this field, and for each of these triangles, the same magnetic field coming out of the plane of the board, same direction, yes or no? See, for example, if you look at this wire, this is my dl, this is my r. So dl cross r at O is coming out of the plane of the board, right? Same magnitude at O. So the total magnetic field will be 3 times this at O. Cos 30 degrees you can replace by root 3 by 2, and that will give me the total magnetic field at O. 3 times B1. 3 times the magnetic field because of one side will give me the total magnetic field at O. Yes or no? Right? Here we have several infinite wires, infinitely long wires, each placed parallel to the y-axis. The first one at x equal to 1 meters, the x equal to 2 meters, x equal to 4, 8, 16 in GP, right? I want to find the net magnetic field at O because of each of these wires. Now, magnetic field at O because of this is going to have a magnitude mu naught I divided by 2 pi into 1 by 1, 2 pi r, 1 by 1, right? And it's going to be, see, if these are my dls, if these are my dls and these are my r's, then do you realize that dl cross r comes out of the plane of the board? dl cross r comes out of the plane of the board. So this produces field out of the plane of the board. This produces field into the plane. This produces out. this produces in, this produces out, this produces in, and so on and so forth? Yes or no? Because currents are in opposite directions. All upward currents will produce fields out of the plane of the board. BOS award, DL cross R. All currents going in the downward direction will field produce into the plane of the board at O. So the net field produced out of the plane of the board at O is going to be mu naught I by 2 pi. The first one is 1 by 1 minus 1 by 2 plus 1 by 4 minus 1 by 8 plus 1 by 16 up to infinity. What is this? Infinite GP series with common ratio minus half. Common ratio minus half. Yes or no? So very clearly this is going to be mu naught I by 2 pi 1 by 1 minus R. 1 by 1 minus R. R is minus half here. Yes or no? That's going to be the net. And it's going to be out of the plane of the board. Because it's positive, I've taken outward positive, so it's going to be out of the plane of the board. Clear? So we have two charges, minus Q and plus Q. And there is magnetic field going into the plane of the board. Alright? And they are separated by a distance d. Okay? I want to find a condition so that the two particles don't collide. Let's first see if they can collide. Okay. One, this is a negative charge. This is V. B is going into. V is like this, B is going into. So V cross B is upwards. But Q into V cross B would be downwards because charge is negative. So this will experience a downward force. It will then execute a circle of this kind with center being somewhere here. O1. Yes or no? Because it's going to experience a force in this direction. Yes or no? This is V, this is B. V cross B is upwards, but minus Q into V cross B would be downwards. So this will be the center of this circle that this will execute, this particle executes. How about this particle? V is like this. B is going into the plane of the board. So V cross B is upwards. So the center of this circular trajectory, O2 would be somewhere here. It will execute a circle, this will execute a circle of radius R1, this will execute a circle of radius R2. That's why there is a prospect of collision. That's why there is a prospect of collision. They could collide, right? Now, if their circles are like this is O1. This is where this particle starts from. This is the center of this circle executed by this particle O2, and this is where the other particle starts from. This is V1, this is V2. This is R1, the radius of this circle. This is R2, the radius of this circle. If this happens, they will not collide. If this happens, they will not collide. Very clearly, this separation is D, isn't it? This diameter is 2R1, this diameter is 2R2. That means for them to not collide, D must be greater than 2R1 plus 2R2. For them to not collide, D must be bigger than 2R1 plus R2, sum of their diameters. But what is R1? MV1 by QB. What is R2? MV2 by QB. So that means D must be greater than 2 MV1 by QB plus MV2 by QB. Magnitude of the radii. So D greater than 2m by QB into V1 plus V2. Right? Then they will not collide.
Is it possible that the two circles are overlapping but still they are not colliding?
Yeah, it's possible. It's possible. You're right. They could, because the point of intersection of the two circles might be reached by the two particles at different instants of time. See, it's possible. That's also possible. He's saying the two circles overlap like this. This is the point where these are the trajectories of the two particles, right? So this is the common point they reach, which is a vulnerable point. If they collide, they will either collide at this point or they will collide at this point. But if particles reach this point at different instants of time, they will not collide. They will not collide. If they reach the common point of intersection of the two circles at different instants of time, then they will not collide. Right. Is a 1 meter long wire, thin wire, carrying a current of 1 amperes, placed in the XZ plane. And there is a magnetic field B, which is 2 Tesla along the y-axis. The coefficient of friction between this wire and the XZ plane, the surface of the XZ plane, is given to be 0.2. The mass of the wire is given to be 2 kgs, the length is 1 meter. We want to figure out what happens to this wire. Does it get accelerated on application of this magnetic field? Hey, first of all, what's the force acting on this? BIL? Because see, we have this is the wire. DL is like this in the direction of the current. B goes into the plane of the board, right? B goes into the plane of the board. This is my DL. What would be the direction of the magnetic field? See? This is DL. B goes into the plane of the board. So DL cross B is upwards. So magnetic force is going to be upwards, and that's going to be BIL. So BIL, these many newtons. Let's see how much this turns out to be. 2 into 1 into 1. That makes it 2 newtons is the magnetic force. Now, there is friction between the XZ plane and this. Let's figure out if this 2 newtons is larger than maximum static friction or smaller than maximum static friction. Very clearly, F max, maximum static friction, is mu times n, mu times mg in this case. Mu is 0.2 into 2 into 10. These many newtons, 4 newtons. So friction will support it. Friction therefore will be able to balance 2 newtons because it can go all the way to 4 newtons. So friction of 2 newtons is a possibility, and therefore this wire will not accelerate. It will not move at all. Yes or no? Thanks so much. Bye. So we have a fixed inclined plane, and there is a conducting rod carrying current I going into the plane of the board. L is the length of the rod, m is the mass of the rod, and what's given is 2 things. 1, the rod is moving down with a constant velocity v. The rod is moving down with a constant velocity v. And that the magnetic field applied is vertically upwards. We do not know the magnitude of the magnetic field. We want to be able to find the magnitude of the magnetic field. What do I do? First of all, realize that this is a current carrying wire placed in a magnetic field. There has to be a magnetic force on it, right? So DLs are like this, B is like this, so DL cross B would be like this. Magnetic force FM would act this way, and that's going to be BIL. BIL is the magnetic force. What are the other forces acting? There is obviously mg acting downwards, and mg could have been resolved as mg cos theta this way, and parallel to the plane we have like a mg sin theta, right? And of course there is normal reaction n from the plane. There is normal reaction n from the plane, right? The normal reaction obviously makes an angle theta with the vertical. This is theta, this is theta. Now, if it's moving down with constant velocity, what can you conclude? Simple conclusion. Net of all forces acting must be 0. Very clearly then, in this direction, n must balance mg cos theta, right? And therefore there must be something that has to balance mg sin theta. Look, this is theta, 90 minus theta, this has to be theta. That means Fm cos theta must balance mg sin theta. Yes or no? Right? Fm, which is the magnetic force, BIL. Fm cos theta, this is Fm cos theta. And that must balance mg sin theta. And by the way, its normal reaction does not balance mg cos theta. Normal reaction must balance mg cos theta plus Fm sin theta. So just to fix that mistake I made, n must balance mg cos theta plus Fm sin theta. So that's as far as direction perpendicular to the plane is concerned. Parallel to the plane, mg sin theta must balance Fm cos theta. Fm cos theta must be taken care of by mg sin theta, right? And therefore there we have a direct value of B available, which is like mg tan theta by IL. That's the value of the magnetic field. That's the value of the magnetic field. Yes or no? Thank you so much. there is a particle, let's assume positive charge q mass m, and moving in the positive y direction at time t equal to 0 starting from the origin with a speed v naught, and is subject to two fields: an electric field, constant electric field of magnitude E along the x-axis, or constant magnetic field B also along the x-axis. We want to find the time after which the speed of the particle becomes 2v naught. The speed of the particle becomes 2v naught. Hey, if the electric field weren't there, then this velocity and magnetic field together will connive to produce a circular trajectory, and that circular trajectory would be such, you know, that's going to be in the yz plane, because if B lines are all along the x-axis, then the plane of the circle will be the yz plane, right? The magnetic field lines will cut that circle normally or perpendicularly. That means in the yz plane, see, V cross B, the center would lie into the negative z direction at this instant of time. So there is going to be circular motion of this kind, right? But this velocity in the yz plane, will keep changing direction, agreed. It will be circular, it will be along the tangent to that circle of radius r equal to mv by qb, but will not change in magnitude, because magnetic forces will not change the speed, because magnetic forces can't do any work. But along the x-axis, there is going to be acceleration. So in the axial direction, the acceleration is going to be QE by m. Q is the electric force divided by mass. That's going to be the acceleration in the x direction. Now that's going to build up velocity in the x direction. So then what happens when the total velocity becomes v naught? What happens when the total velocity becomes 2v naught? Hey, there is a velocity component in the yz plane which remains v naught, so v naught squared plus velocity in the x direction becomes vx squared, and that must be 2v naught squared after, right? This v naught is what? Velocity in the yz plane. What is this? This is velocity in the x direction, right? And that must become equal to 2v naught whole square. I want to and this vx, why is this changing? Because there is acceleration in the x direction. So after a while, the velocity in the x direction becomes like a root 3 v naught, 4v naught squared minus v naught squared, root 3 v naught, and with acceleration ax equal to qe by m. So this happens in time t, where vx must be ax into t. Time taken is t naught, so t naught is going to be root 3 v naught divided by ax. Ax is qe by m. That's the time taken for the total velocity to become 2v naught in magnitude, right? However, the velocity in the yz direction, see, any motion, the circular motion in the yz direction is because of this v naught and magnetic field in the x direction, and that cannot change the magnitude of the velocity. However, there is acceleration in the x direction because of the electric field, so velocity in the x direction grows. So after a while, this is v naught, which is the velocity in the yz plane, plus velocity in the x direction square is this, and v equal to root 3 v naught, which must be at naught starting from rest. Yes or no? Because initially there was no velocity in the x direction, so v equal to 0 plus ax into t naught, and that gives us the value of t naught, right? In this problem, we have a particle of charge to mass ratio alpha starting from rest at the origin, is subject to two fields, a magnetic field B naught K and an electric field E naught I, uniform electric and magnetic fields. It's found that when the particle reaches x naught 0 0, the velocity of the particle is this. We want to find the value of x naught. Very clearly, the electric field is a conservative field. No matter how the particle moves, the net work done by the electric field is going to be QE naught into x naught, displacement in the direction of the electric field, and that must be change in kinetic energy. So that must be half of m into v squared, square of the velocity. This is magnitude of the velocity, as you can see, is root 3 square plus 4 squared, which is 5 meters per second, right? So this is into 25, 5 square, right? So then we can replace q by m by alpha. Alpha E naught x naught, right? This m I can bring in here, and then q by m is alpha. Alpha E naught 2 alpha E naught, or rather x naught is 25 by 2. Q by m is alpha E naught. That's x naught, right? X naught is going to be 25 by 2. Q by m alpha comes in here into E naught. That's the value of the x coordinate of the particle. Thank you.